We have sort of a resting membrane potential that comes out to about 70 millivolts. Now remember, milli is a prefix that tells you 1,000ths. So when we talk about milliseconds, we're talking 1/1000th of a second. If we're talking millivolts, we're talking 1/1000th of a volt. Okay? So basically, the resting membrane potential, the membrane is polarized. You have so many positive charges outside, so many positive charges inside, so many charges of negative outside, so many negative inside. So what you end up having is that overall, when you add up all the charges, you have a net of a positive outside charge and a negative inside the membrane charge. The membrane acts as a charge separator. It's like an insulator. So the sodium ion concentrate is greater outside, potassium ion concentration is greater inside. The concept of depolarization, that is where the cell interior polarization is slightly less negative. And we measure everything by what's going on inside. We usually with an electrode to get an idea. A depolarization is usually a localized event, but if the depolarization is strong enough, it spreads along the membrane in all directions. Now, to help you understand that, you take a look here on this chart. Resting membrane potential for this particular membrane, minus 70 millivolts. When you get up to minus 55 millivolts, and these would be from small depolarizations, once they hit this is referred to as a threshold. This will initiate sodium ion channels that are voltage gated. They will pop open and you'll have this massive flooding inward of positively charged sodium ions. And this is referred to as depolarizations. And you can get such a depolarization going from minus 55 all the way up to almost plus 30. By the time you get up to about here, the sodium ion channels begin to close and the potassium ions begin to open. When they do, they're kicking out positively charged ions. And so what happens is you start having this repolarization effect. In other words, the membrane potential starts going from minus 30 to minus 29, plus 29, plus 25, 0, minus 10, minus 20, etc. Eventually, the potassium channels will close, but usually this is after you've achieved almost this hyperpolarization. Roughly around where my needle pointer is minus 75. How do I get this reestablished to a minus 70? Remember the sodium potassium pump? Yeah, that guy. That's the pump that exists, and we went over this, and I encourage you, if you need to review it in chapter 3. The sodium potassium pump takes sodium. It's a pump now, so it's going to require ATP. It's going to require energy to pump this. It takes sodium from the inside of the cell, kicks them out. It takes potassium from the outside of the cell, kicks it in. And so what's going to happen is it is going to help in reestablishing the proper depolarization balance at minus 70. Now, before I go on, there are a couple of other points you need to be aware of. I already talked about at the neuromuscular junction, you have this release of the neurotransmitters that are held in these little vesicles that by exocytosis fuse and release into this space called the synaptic cleft. And in the synaptic cleft, acetylcholine travels over, acts on these ligand-gated channels. Basically, these are ion channels that once acetylcholine attaches to them, sodium rushes in, potassium rushes out. You have a wave of depolarization. This travels up until you get slightly farther from the synaptic cleft where you have voltage-gated sodium channels and voltage-gated potassium channels, and they will start to open and close, creating now the action potential, which is a much greater depolarization wave. This wave spreads out. Okay, I got a question for you. What stops the switch? If I've got acetylcholine in the synaptic cleft, what happens to it? Does it stay there permanently? Does it take a vacation? Does it stop after a while attaching? No, it's still there. As long as it's there, it continues there. What happens is we have an enzyme present in this membrane, in this synaptic cleft, called acetylcholinesterase. This will break the acetylcholine neurotransmitter to acetyl groups, acetate groups, and choline. The choline will be taken up again by this axon terminal to be made into new acetylcholine. The acetyl group kind of floats off. But, and this is particularly important for all of you healthcare nursing people, what stops the enzyme? Well, it would be a disaster if you have the enzyme stop, because what happens is you keep having the switch on, the message to keep the muscles contracted, and you can't stop it. And what happens is that pesticides, particularly organophosphate pesticides, and nerve agents, block the activity of acetylcholinesterase. You probably have heard nerve agents in the past year or so. Big discussions about it. Russian former agent, was killed by a nerve agent. The half son of the North Korean dictator had some people kill him, that half son, or excuse me, half brother, I should say, with nerve agent. They just splattered it on his face. Now, probably what they did was they had gloves. And one came in and gave one component of the agent, the other one gave the other component, and within 20 minutes, that man was dead. Okay? And they did not understand what was being put on his face, and it absorbed fairly quickly and shut down all of his body functions. Okay? So, what would be the effect of a nerve agent on the muscle? It would be permanently contracted, because without the functioning acetylcholinesterase, these pesticides and nerve gas agents, they paralyze and shut down the function of the enzyme. The enzyme's not functioning, the breakdown of acetylcholine can't function, and so you've got, in essence, the switch to, say, contract the muscle permanently on. It can't be reversed. Okay, so that's the review of the neuromuscular junction. Before I go further, though, I wanted to bring up one or two other points here. And that is, if we go back, I've talked about the acetylcholine receptor, and I've talked about the synaptic cleft, and I've talked about the neurotransmitter, and I've talked about the depolarization that occurs. Now, here's another very, very important point. It's a medical disorder called myasthenia gravis. This is an autoimmune disorder where the number of acetylcholine receptors decline, that is, are reduced, resulting in muscular weakness and the failure of muscle contractions. What do you mean by that? Well, an autoimmune disorder is when you have your immune system acting on normal tissue, and the immune system will destroy that. Now, that's usually a malfunction in the immune system. But here's the bigger problem. The immune system will target the acetylcholine receptors, and without the acetylcholine receptors, there's no way to stimulate the muscle contraction. Without the muscle contractions, and remember, some of the muscles that are skeletal muscles assist in your capability to breathe. The intercostal muscles between the ribs and that big sheet-like structure called a diaphragm. It is those structures that work. They're made of skeletal muscles. They are dependent upon acetylcholine and the neural stimulus to function. Without that, you ain't breathing. You ain't breathing, you dead. Ta-da! I know. I should take it more serious. Sorry about that. The main point here is that this is a sad disease where the immune system continues to destroy the acetylcholine receptors. Well, doesn't the body make more of them? It does to a point, but it's usually not that fast. And eventually the immune system begins to destroy more and more of them. And eventually the muscles do not contract, or they first show up with weakened contraction because they get less and less of the receptors that are present being stimulated. And eventually the immune system destroys all of them. The body isn't able to recover and make more of them fast enough. And the person has major malfunctions and failures of muscle movement, being able to maintain posture, of eventually being able to maintain breathing, and they die. It's very sad. Curare, though, I want to bring up another point. This is a poison that was extracted from the skin of the South American frogs. You know all those little frogs that they sell in stores and science museums. They're really brightly colored, the red with the black mottling, or the yellow, or the green ones, or the blue ones. And kids go, "Ooh, froggy, really cool." Well, in the skin of those frogs is a product called curare, and it's used in medicine to suppress breathing or voluntary muscle contractions. Anesthesiologists will use this sometimes in very limited dosages to control the breathing or to assist a patient to be put onto a respirator. Now, granted, the drugs in small amounts can be controlled to basically suppress breathing for a while until the surgery is done, and then basically the effects will wear off. Okay? Now, well, how does this work? Curare, interestingly enough, blocks the acetylcholine receptor. So it blocks the binding site on those receptors where acetylcholine would bind, and therefore it blocks the acetylcholine signals. Okay? All right. At this point, I wanted to see, and we have covered a good amount of this. Now, I will take time on Tuesday and go over more of this. I want to stop at the motor unit at this point. What I encourage you to do is to print off the lecture notes. We'll go over them. You don't have to worry about that on Tuesday. And again, also for those that were concerned about the exam retake, we'll retake it on Tuesday after 12 noon. For a few of you, you've asked to take it in the morning. That's okay too. Um, and I'll have probably on Tuesday tell you what room we will have. Also, remember that we will have this coming up week, the week of the 12th, basically the lab practical exams. Until then, I hope you have a nice day and stay warm.